So I've got two linear motors here. They're coupled together with a very stiff coupling. So if I move one motor, the other one moves. I had to align these two motors using a precision plate, assuming like all the holes that are used to mount the motors together are very precise. It's a very rigid structure. So if the alignment was poor, there would be sticky places in the travel. And so the alignment seems to be pretty good because it's easy to move by hand. So we're going to look at the Zenus 2-axis drive doing two motors together in a gantry configuration. First, we're going to talk about straightness, flatness, maybe plum and square. But the definition of straightness has to do with two lines that are in parallel. See if there's a good image of that. Yeah, so, well, there's a straightness between two surfaces. So two parallel lines talks about the straightness. That's very kind of one-dimensional thinking, but it's a good start. So straightness, of course, is important. So the motor is a tubular linear motor with magnets in the rod and a coil that we control the current through. And you'll notice there's a gap between the magnet and the coil. So these two surfaces don't touch. So alignment just has to be sufficient enough here to keep the gap. So what's more important are the bearings. So we can see in this tubular linear motor with the moving coil and a stationary magnet that there's two bearings inside of here. So as the motor moves back and forth, it's important that this bearing alignment is good. So typically precision stage will have good flatness and straightness, and I assume it's plumb, square, and flush too. So installing a door, you learn a lot about plumb and square and flush. Similar is important for a precision linear stage for the alignment of the bearings. And I just love watching this guy work, but he's aligning the bearings here. So he's got one bearing set in as the primary and a second bearing as a secondary. And this is a greater distance, but you can see there's some play in the alignment so that he can get the straightness he wants out of the system. So he can use a tool to measure the distance between the two surfaces. So I guess this to me looks like aligning a straight line, but if everything is square and plumb, that you'd be aligning the two planes. So in order to get the gap to be the same between the two, you have to adjust the bearing alignment to bring it into conformance. So along the way, he'll tighten up at various points along the travel. And I guess, if the distance, it's just metal, so maybe it bends a little bit. So he's got a lever arm on the end, and he can do the alignment all the way down, and the goal is to keep the needle in the center. So in order to get not just straightness but flatness, You have to look at the surfaces and see how they conform over a distance of travel. You know, do they rise? Do they fall? Is it shaped like a potato chip? Is it bumpy? So the mechanical engineer defines the flatness over like an average area, and so the geometric shape would be for flatness, and then the tolerance plus or minus some variation in the two planes. So I think along with the straightness, the flatness of the surfaces are also important, because you can have, you know, things not straight in various dimensions, like flush, plum, square. So straight and flatness. We're going to take a look at setup and tuning using the CME software. And in this actuator, you can see that at the moment both axes of this system are disabled. I've got the two blinking lights for A and the B axes, and I'm going to, I'm already connected. So here's the connection. So what I'm going to do is, this motor is incremental. There's no Halls. There's no absolute feedback. I need to phase the motor. So to wiggle the A axes, I need the B axes to be disabled. I'm trying to enable. I come up in a can mode. I can't enable. So I will select the jog option. I'm not going to jog it, but I'm enabling it for a period of time so that I can phase it. I mean, I can jog negative and positive, and the master axis carries the slave with it. In order to phase the B axis, I need to disable the A axis. So now that I can see the blinking lights and the A axis is disabled, the B axis has not been phased yet. I'll try to enable. I can't enable until it's can. So then I switch to a position mode. So the B axis is enabled, and it does a little wiggle. It finds its phase, and then I can disable. When the A axis and the B axis are both enabled, you need to sort of jog them together, either by sending the same command at the same time, like over can, or you can make the B axis the slave to the A axis. And so I'll do that here. I'm going to change the mode of operation for the B axis. And for doing gantry, besides like a cross-coupling gain feature, we have the B axis can be slave to the A axis. And I'll start off with position mode, and then we'll peel it back to the other modes. So when I make a move with the A axis, the B axis will follow. I'm going to see if I can do some homing on the A axis. I did not enable the B axis yet. Okay, so let's try that again. So that was easy because the B axis was disabled. Not phased yet. Okay, so in order to phase the B axis, I need to disable the A axis, and then go back to the B axis and enable the B axis in a position mode. And then it's phased, so now I can go back to a slave mode. So you can see the mode of operation is slave, and it's slave to the A axis. And the A axis is disabled. Well, maybe I want the B axis to be disabled too. So let's go do that in the basic setup. And so when one disables, you want the other to disable. So this is a new feature of CME 8.2.4 where you can disable the slave when the master disables, and you can disable the master when the slave gets a fault. So if I'll set those two bits, bit 8 and bit 12 of 0x145, and I'm not phased, so I need to disable the A axes, but I need to enable the, I can't enable the B. All right, so did that work? Yes, I took it out of slave mode. I went to a software program mode. But when I'm in a slave mode and I want to enable it, I can't because I have to enable the A axes in order for the B axes to be enabled there. And now I'm going to home the A axes and the B axes will just follow, and we're homed. And now we can move from the home position with both the A and the B axes, given that it's in a slave mode. And we can see distance. Let's make there's a short little move. And I would trace the profile velocity of the B axis, but it's actually the same as the A axis, so there's no point. And you can see that here the following errors are separated by about 100 counts between the two axes, so there's no cross-coupling gain to bring those together. But curiously enough, the actual current is diverging. So the B axis is doing all the work, and then it comes down, and then the A axis isn't doing any current, and then it builds up. So, based on flatness, straightness, and alignments, plus also, the resolution and accuracy between the two encoders are important. But you can see here the currents, the following errors are diverged a little bit. So in this case, because there's a stiff mechanical coupling, if the B axes were to have some integral gain, just like the A axes were to have, I've got the A axes with a 3000 for the integral gain. We might see a slightly different case of the convergence or divergence. So both have good integral. Again, if there's very stiff mechanical coupling between the two axes, your currents can fight each other. So here the actual current is at plus 5 amps of this guy, and the B is at minus 5 amps. So there's no work being done. They're just fighting each other. The currents do settle down a little bit after motion, but that's because of their integrators. So again, I'm going to go back in and I'm going to reduce. I'm going to let the master axes be the tiger, and the B axes I'm going to make it a cub, so that they're not fighting each other. Oops, I moved the B axes. Didn't want to do that. And let's see if I can. There. Good. So hopefully their currents have settled down. So I got minus 0.3 amps on the A, and the B axis is also at a low. Well, it's kind of hunting a little bit. But what we can do to remove the divergence of the current, of course, and not worry about any following error between the two, is we can make the B axis the current slave to the A axis. And that way the currents in both axes will be exactly the same, and we're just not at all monitoring the position